resume with a talk by Gregory Wilsenach on extending symmetric circuits.
Hello everyone, good afternoon. So I'm going to talk about extending symmetric circuits. So in particular that means I'm going to talk about extending work by Anderson and Dewar and their work on symmetric circuits and capturing fixed point counting. Very importantly, my work's going to not only extend their work, but my talk's actually going to extend Matt's talk. So Matt Anderson today spoke about symmetric circuits, and I'm going to very crucially rely on his introduction, because otherwise I don't have anywhere near enough time. Anyways, and also I'm told that the first results of the election will come out between now and the end of this talk. So if anyone wants to ask a question that encodes information about that, that'll be great. Anyways, so the talk's structured into three parts. First, I'm just going to quickly discuss some background on the actual problem of capturing polynomial time with logic, just so that I can justify the introduction of sort of candidate logics. And then I'm going to talk about Anderson and Dewar's symmetric circuits and their attempts to understand that problem. And then I'm going to talk about how Anush and I have sort of worked on extensions to that circuit model to try to see what we can. So there's this very central problem probably the central problem in descriptive complexity of trying to find characterizations for polynomial time, sort of capturing problems for capturing polynomial time. And the sort of first big result in this was by Immermann and Radtke, the sort of very famous theorem that on ordered structures, fixed point suffices. But of course, fixed point fails hopelessly when you try to expand past ordered structures. You can't even do basic things like parity. So in response, Immermann conjectured, well, perhaps fixed point with counting might work, solve this sort of counting problem directly. And the result was fixed point with counting was quite studied and turned out to be this really great logic which captured an awful lot of what we think of as polynomial time, what we think of as sort of obviously polynomial time. So it expressed sort of very obvious polynomial time problems that were P-complete, so things like the circuit value problem, and sort of far less trivially, it contains things like maximum matching, proved by Anderson, Dewar, and Holm quite recently. That's the other Anderson. It also has been used, it is the other Anderson. Anyway, it's also been used for capturing results, or partial capturing results on polynomial time. So things like capturing polynomial time over particular graph classes. So probably the biggest result in this was by Groa in 2010 that works on any proper minor closed class of graphs. Unfortunately, however, fortunately or unfortunately, FPC turns out not to do the whole of P times. So the CFI query by Kaufmann and Immermann acts as a counterexample, something trivially, well, not trivially, something computable in polynomial time but not expressible in FPC. And later work by Atsarias, Bolotov, and Dewar showed that in actual fact there's a rather deep connection between these CFI queries, and they really are plural. Although the initial one was constructed, it turns out that you can really find a family of CFI queries. But anyway, they show that there's really an intimate connection between these problems of these CFI graphs and solving systems of linear equations over finite fields. And in actual fact, they extended to systems of equations over groups and rings and other algebraic structures. In any event, this leads on to this problem of trying to find what are called candidate logics of polynomial time. That is to say, logics strictly more powerful than FPC, but yet not known to contain the whole of polynomial time yet. The end goal being finding one that characterizes the whole of polynomial time. The first and really interesting one is called choiceless polynomial time, developed by Blas, Gorovich, and Scherlach in 1999. And it's defined in terms of what are called BGS machines. Now, going into detail about what a BGS machine would take an awful long time, but the basic idea is this. A Turing machine takes in an encoding of a structure, and in doing so, it sort of implicitly orders it. And what we'd really like to do is study what computation looks like on sort of pure structures. So their BGS machine directly takes in an unordered structure. It operates on hereditary finite sets over that structure and has access to parallelism, but very, very importantly, can't make sort of arbitrary choices. So in some sense, it can't make choices which violate the symmetries of the input structure. And CPT, choiceless polynomial time, is then exactly what you'd expect. It's BGS machines, but with polynomial bounds imposed. Now, it's not too. They showed, I think, in their original paper, or perhaps a paper just after, that CPT contains fixed point with counting, and can compute the CFI query. So it is strictly more powerful than FPC. And in actual fact, it can compute the CFI query even if you take CPT and without its ability to count. So it's really powerful. It's not known at the moment whether it can do linear equations, solve systems of linear equations, but more on that later. Anyways, the next logic that was considered was rank logic, which is a far more direct attack. It takes systems of linear equations, throws in something to solve that problem. So it was proposed originally by Dwyer et al. And in 2009, but there was a slight complication. So in the end, in their paper, rank logic is dead, long live rank logic. Gradle and Bakuza slightly tweaked it. And when I refer to rank logic, I'm referring to their version. Anyways, rank logic just takes fixed point logic with counting and throws in this rank quantifier, which takes in a formula which defines a matrix and some prime and computes the rank of the matrix in the field of characteristic P. And obviously, it can solve systems of linear equations, and it can also deal with the reductions, so therefore it can deal with CFI queries. Okay, so we end up with something that looks pretty much like this. The strict containments I've explained, and the containments inside p-time are not hard to prove. The interesting thing is simply this middle bit. We have absolutely almost no idea what the real connection between fixed point with rank is and CPT. Anyways, so the next thing I'm going to talk about a little bit is the circuit model that Anderson and Dewar introduced. So I'm going to rely heavily on Matt's talk. I'm going to assume most people here went to Matt's talk and are really comfortable with that. So essentially, they introduced these circuits. They choose a particular basis, usually the ordinary basis and or not, or else that with some majority gates. And they simply have input gates. So for the moment, suppose that we're taking in a graph. We'll simply have gates for every potential edge in the graph, a couple of constant gates. Then we have a collection of the internal gates, which are labeled with elements from our basis, our Boolean basis, and then we have just an output gate. So Matt also defined the notion of an automorphism of the circuit, so exactly what you expect, a structure-preserving map on the circuit from the circuit to itself. And importantly, Anderson and Dewar dealt with two properties of circuits, the first being invariance. So in other words, the circuit computes an actual graph property. The second being symmetry, which is the interesting one. The idea being that in this case, every permutation of the input, and in particular the input gates, should induce a permutation. Should extend to a permutation on the extend to an automorphism on the entire circuit. Right? And in actual fact, they proved that this property is decided by any property that's decided by p-uniform families of symmetric circuits is in fact expressed in FPC. So these two notions are equivalent. Initially, they actually attempted to capture the whole of CPT, but ended up with this result. Anyways, I need to quickly go over at a very high level, go over how their proof was structured, simply because we're going to make use of it a little later. So I think Matt went through it in a lot more detail. So I'll be referencing his talk here as well. So the easy direction is taking FPC formulas and producing symmetric circuits. In that case, you just do the ordinary trick. Existential quantifiers become large disjunctions, universal quantifiers large conjunctions, and you can deal with FP as well. The hard direction is going in reverse, taking symmetric circuits and producing, uniform families of symmetric circuits and producing FPC formulas. So in that case, the real powerful ingredient is this notion of a support and a support theorem. So they take a support is simply some set S over, let's say the inputs are labeled 1 to n, and we're thinking of input structures as being structures over the universe from 1 to n. And support is just something, it's just a set such that every permutation that fixes that set pointwise fixes the automorphism. An automorphism extended from that permutation fixes the gate G. Right? And their proof is structured as follows. They prove that all gates that have constant size support, prove that so long as the circuit family is P uniform, you're going to end up in P uniform and symmetric, you're going to end up in a situation where every gate has constant size supports. And then in parts 2 and 3, they essentially, they use that notion of that constant size support to encode all the information they're going to need to evaluate a gate for any particular permutation of the graph, and they use that and the fixed point operator to actually construct an FBC formula equivalent to the family of circuits. But the point I'd really like to emphasize in this slide is just that first point: prove all gates in the circuit have small constant size support. Right? Small or constant size support. That's the actual important ingredient here, and that's the bit I'm going to have to reference a bit later. Okay, so we have this notion of a symmetric circuit that Anderson and Dewar introduced, but the real trick is actually now trying to extend that notion so that we can get something more useful. So we have that they capture FBC. Perhaps we can try and extend it in such a way as to capture CPT or perhaps even rank. And we're going to look at two rather straightforward ways of extending the notion of a symmetric circuit. So the first way is you might just take the symmetry condition and weaken it. So an obvious way of doing that might be, the requirement is that for every permutation on the input you have an extended automorphism. Perhaps you limit that to only a few permutations on the input. Another approach is you simply change the basis. Take the basis of functions you allow a gate to compute. Take the functions you allow a gate to compute and throw in something more powerful. So the first approach we looked at was weakening symmetry. And for the moment, let's just take a step back and think about the relationship between symmetric circuits and sort of the ordinary non-symmetric variety. So suppose we have a family of P uniform invariant Boolean circuits that recognize some graph property. So that's what I mean by invariant Boolean circuits. We could symmetrize them in quite a straightforward way. So we could imagine taking every gate and sort of throwing in the orbit of that gate. So let's suppose the gate was connected to the input gate 1, 1. We could take all permutations of that and simply just throw in copies of this gate at the appropriate places. So sort of add in the orbit. So we can take a family of circuits and symmetrize every one. And clearly, if that family was still polynomial, then it meant that our original circuit was just computing something in FBC anyways. But perhaps we can change that. So our approach was, perhaps we can actually take that family, and instead of throwing in the whole orbit, throw in some partial bit. And in particular, what we'd like to do is we'd like to sort of take inspiration from CPT, from choices polynomial time, and the BGS machine, where the symmetry isn't for any structure of input n. The symmetry requirement in CPT is really a symmetry requirement for a particular input structure. So we'd like some input structure aware symmetry requirement and see if that can perhaps extend the power of these symmetric circuits. So let's try and formalize that. So suppose we have a structure A of size n, and in particular, let's, for simplicity, just suppose the structure A is over the universe 1 to n. So that makes encoding it into the graph really straightforward. We don't have to worry about encoding individual elements. So let's take the encoding of A, or the sets of to be the set of all encodings of the structure in n. So every possible way of every isomorphic copy of A inside that set. Every isomorphic copy of A with the same universe. Now let's think about all permutations. All permutations of the input, which for a particular structure A and a particular gate G, keep G constant for all isomorphic copies of our structure A. Okay. So we're going to call that the invariance group of G with respect to A. And the idea here is that this invariance group, or taking the index of this invariance group in the symmetric group, is going to be a bit like taking the index of the orbit in the stabilizer in the symmetric group. So it's going to be something reminiscent of the orbit, but this time with reference to some structure. And similarly, we're going to bound these, for every structure, we're going to bound this orbit notion by some polynomial. So here for any arbitrary P uniform family, circuit family and a polynomial P, we want that for every structure, this sort of the order of this invariance group of G with respect to A in the symmetric group is bounded by a polynomial. And we thought this would really work. We thought this was a much more powerful notion, but it turns out that this family of circuits can't do the CFI query either. Okay, so we ended up proving that it certainly doesn't capture CPT, but it may or may not be a more powerful model. We have to still check. But let's look at the other approach of expanding the basis which you're actually computing over. Okay. In this case, let's just start with a rather obvious observation. Anderson and Dewar in their characterization essentially prove that symmetric circuits with majority are much more powerful than symmetric circuits without. One can think of it a bit like the situation with constant depth bounded polynomial size circuits in the ordinary Boolean case. In that case, throwing in parity gates makes them provably stronger. What we might want to do if we're going to think about adding in functions is first ask, well, what functions might actually improve the power of the model? And it turns out if we are considering symmetric functions, that adding in symmetric functions to the Boolean basis does nothing. You can add in as many symmetric functions as you like, so long as you've got majority functions. So long as you've got majority gates, you're not increasing the power of the model at all. I should stop here for a sec and say, I'm talking about symmetric circuits and symmetric functions. And of course, they're entirely different notions, right? Symmetric functions are functions where any arbitrary permutation on the input, the function has to remain constant. In other words, the function only depends on the number of ones in the input. And symmetric circuits are an entirely different notion. I'd love to use two different words here, but unfortunately, this is how everyone says them, so it might read in a slightly confusing way. Anyway, so it turns out that for any family of circuits of a subset of symmetric functions, you can find an equivalent family of circuits with only a polynomial size blowup with a standard basis of majority. And the proof approach is reasonably straightforward. The only slightly tricky thing you have to think about is the fact that you have to make sure everything is implemented symmetrically. So perhaps we should look at adding functions to the basis that are less than symmetric. So aren't actually symmetric functions, but are perhaps structurally something symmetric. And of course, we're actually thinking on the side about rank logic, so we considered adding matrix symmetric functions. In this case, an input is structured with the input is structured as a matrix, and instead of requiring that the function is constant over any arbitrary permutation of the input, we say the function must be constant for any permutation of the columns and rows separately. And of course, the obvious example of a matrix symmetric function is a rank function. And what ends up happening is, what we ended up doing was proving a support theorem for symmetric circuits with matrix symmetric gates. So take the ordinary basis, throw in these additional, or allow these additional matrix symmetric gates on top of symmetric functions. And in actual fact, we can prove that in the event that the circuit is, well, this is going to imply immediately that in the event that the circuit is p-uniform, you're in a situation where every element of the circuit has a constant size support. And by plugging that into the proof that I mentioned earlier, we ended up being able to prove this, that p-uniform families of symmetric circuits with rank operators are in fact the same as fixed point with rank. I should say, that shouldn't say just any complete basis. Let's just take the ordinary basis for the moment, so and or not. So let me just quickly conclude and sum up what I talked about. So we have this problem of p-time, and from this problem of capturing polynomial time, we end up with two really interesting logics to study, CPT and rank logic. And Anderson and Dewar attempted to study these logics, in particular CPT, and ended up developing this notion of a symmetric circuit, but it fell short of capturing CPT. We studied methods of trying to extend rank logic, and ended up showing that some natural extensions which we thought might capture CPT failed, but that there's an extension of symmetric circuits which does capture fixed point with rank, which we think is quite interesting. Anyways, any questions?
Questions?
So I think that gets the definition of what precise gates do you throw in? Any kind of matrix symmetric gates?
Yeah, so any kinds of matrix symmetric gates. Well, so for the support theorem, you throw in any kind of matrix symmetric gate. And of course, when you're concretely going to the rest of it, you throw in a rank gate. There's a slight trickiness in that you really have to actually change the notion. So, I mean, it's more complicated than that. You really have to go through and change your definition of the circuit to actually allow you to label the inputs. There are slight subtleties there. But yeah, matrix symmetric gates.
Yeah, but what puzzles me with that, no matter which kind of matrix symmetric gates you throw in, you always get rank logic.
No, so in the case of the support theorem, all I'm showing is if you throw in any symmetric gates, you're still going to get small supports.
Yeah.
But then, of course, when you go through the rest of the proof, you actually have to be very specific about what you're throwing in.
Do you have to just for rank gates, or I mean, there are other kinds of
Yeah,
gates,
so that would be very interesting.
membership or whatever, and
So we haven't explored what would happen if you threw in other gates and what it would look like. In particular, what we'd really like is, so we have this notion that in the case of symmetric gates, you have this like sort of complete notion of a majority gate. Once you have a majority gate, you've got all the symmetric gates. So the question would be like, well, what's the equivalent notion for a matrix symmetric gate? Is there like some gate you can throw in, and once you've got that, you've got all the matrix symmetric gates? And I think Anuj has a mock of a proof of that.
So yeah, just to clarify, so the support theorem is proved for any matrix symmetric gate, and then you use that to show that if you only use rank gates, you can translate it to rank logic, right? And so yeah, the question is rank gates enough to do all matrix symmetric gates? And I have an argument that if that were true, then fixed point with rank could do all of p time. But
I'm also going to give you the permanent too, right?
sorry.
You could also do the permanent if we were talking about that.
No, I mean, let's say polynomial time matrix symmetric gates, right? I mean, it's.
yeah, but I mean, there are these problems that I mean, nobody really believes that rank logic captures polynomial time, and I mean the question is, rank seems not to be helpful for solving, say, linear equation system over rings, for instance, which are also in polynomial time. But there is no reasonable notion of rank over rings that would be polynomial time computable and or help to solve linear equation system. So this is very unlikely. But the question is whether there is a, let's say, a uniform kind of theorem that would not just for rank logic but for other variants. I mean, I think group membership, permutation groups is an interesting.
No, but that I think this does address, in the sense that because the support theorem works for any matrix symmetric thing, that means that pretty much for any matrix symmetric operator, you add it to the fixed point logic and you add it to the circuits, and you should still get the equivalence.
So you get
that kind of thing should work out. But okay,
Well,
Greg's doubtful. But
Well,
anyway.
no. I mean, the support theorem definitely works fine,
Yeah,
right?
yeah,
The rest of it, I'd have to make sure that it actually goes through the rest.
I think.
Any other questions or answers to?
Yeah, answers to questions would be good too.
I think a question. No?
Okay, great.
Okay, so let's thank
Thank you very much.